just heard easily the current state of the art in optical physiology methods in these last three talks. What I'm going to talk about today is large-scale mapping of brain activity using electrical methods. And compared to, where's our laser pointer here? The optical physiology methods have exploded in terms of their scale and capacity to record from thousands of neurons in the past 5 or 10 years. And although I'm a biologist by training, the electrode technologies of recording electrical activity of cells haven't really advanced as fast. If you actually have a look at from when the first single electrode studies were done in the 1950s, through to present day, the number of simultaneously recorded cells that have been recorded extracellularly, has roughly doubled every 7 years, to the point that in at least larger animals, it's possible to record from sort of 1 to 300 cells simultaneously. Far less than the 80,000 cells that we've been hearing about in these new techniques, but with much greater temporal resolution and the ability to record from deeper structures or disparate structures in the brain. So I'm a biologist by training, but this sort of slow progress was what motivated me to get involved in doing some technology development over the past few years, both at Berkeley and continuing that at the Allen Institute. So this is our lofty goal, and we have I guess we have 2 months here to get here. And so maybe I should update that. But I will discuss the developments that in recent months that show we've got very close to this goal here of an order of magnitude increase in the number of simultaneously recorded cells using electrical methods. So the challenges to doing this, this is the goal. We want to record from thousands of neurons simultaneously with high temporal resolution and from deep cortical structures, not just on the surface of the brain. Ideally, we'd like to look at a sampling of high-density recordings in multiple brain areas. Do it in both acute and chronic implants so we can study behavior. And also, as we'd heard earlier today, do localized optogenetic stimulation to do perturbatory type experiments, causal experiments, to test our hypotheses about neural coding. The challenges for doing this electrically are manyfold. The current electrode technologies are limited to roughly 64 channels due to the size of the lithography that's used, and the commercially available electrodes become increasingly invasive as the number of channels increases. It's a big challenge to get these signals relayed off the brain if you have 1 wire per electrode. The cost of recording equipment until very recently was very expensive. The popular animal models, mice, transgenic mice, really limits the size and weight of instrumentation you can put on the animal if you want to study behavior. And also the cables that are required to record these signals in an awake-behaving animal become very restrictive. So this is our approach to this problem that we sort of started as part of an NSF grant in collaboration with my colleagues at Berkeley about 3 years ago. And we looked at sort of 3 things we wanted to improve. One is improving the electrode technology, making them smaller with more channels and less invasive. The interconnects between the electrode technology and the recording electronics for amplifying and digitizing the signals, which we also wanted to make modular, scalable, and much, much smaller than what was currently available commercially. And we wanted to make them cheaper in volume and so on and so forth. First, the electrode technology, just zooming in on one of these electrodes, it comprises a silicon electrode here that's on the order of about half a human hair wide, about 25 microns thick, and has up to 128 channels on the electrode. Flexible interconnects that allow the electrodes to be placed, a very, very small cable, very flexible cables, about 6 microns thick, that allow multiple electrodes to be placed in adjacent brain areas without putting tethering forces on the brain. And also, this is the interface to the recording electronics that also includes some optical stimulating components, which I probably won't have time to talk about today, but are in the works. These are examples of the different probes. Each one of these little dots here is a different electrode. So they vary in terms of their spatial layout depending on how much of the brain you'd like to record from and how high density you'd like the channels. It's a trade-off between the number of, the ability to isolate the signals from individual cells versus the amount of brain you can cover with a finite amount of channels. But through the efforts of a very talented postdoc at UC Berkeley, Mason Chamanzar, he's been able to get the lithography in a university lab down to 250 nanometers, which is really the limit of deep UV lithography. What that means is we can make the probes no wider than we have to for the configuration of electrodes we want to lay out. So these, typically the NeuroNexus probes, the probes that are currently available, the width of this shank and the damage that it does in the brain is determined by the width of these tracks for getting the signals off the electrode. Another aspect, improvement in this technology to attempt to double the recording volume without increasing the damage is to make these recording sites basically with a punched via, like a printed circuit board via on the scale of 10 or 15 microns here, and then filling that little hole with conductive polymer. This effectively makes the electrode able to record from both sides of the electrode and doubling the recording volume without doubling the damage or the invasiveness of the device. To give a comparison of the flexible cables that are currently available, here's an example of a 64-channel multi-shank probe from NeuroNexus. The cable is made of polyimide and is fairly, it's flexible in terms of printed circuit boards, but compared to the brain, it's essentially rigid. This is against one of our devices here, where the cable is far, far smaller. It's less than 0.5 millimeter wide, 10,000 times less stiff. And the hope is that not only can we put these, well, firstly, not only can we put these much more closely spaced in adjacent regions of, say, the visual cortex in the mouse brain, but in chronic implants, the hope is, and these studies are ongoing, that the recordings will be much more reliable than is currently possible. What typically happens with these devices is they stop recording from neurons after several weeks after they were implanted. Okay. In terms of the electronics, these are examples of some of the commercially available amplifiers and digitizers that are on the market at the moment. The best of these have up to 128 channels and are really too large to fit on a mouse head. So we developed a head stage that is 1 square centimeter in size and weighs, is essentially modular, where you can add 64-channel modules in a vertical stack such that with 1 cubic centimeter and 1.3 or 1.4 grams, you have a 256-channel recording system. In addition to that, the signals are multiplexed both in analog domain down in each one of the amplifier modules, and then sent up to another multiplexing stage where you only have a 6-wire tether that's 0.5 millimeter in diameter for up to 1,000 channels. So we get around the problem of tethering the animal with a 1,000-channel cable. This is achieved with chips from Reed Harrison. This is an example of the chip here, which does the buffering and multiplexing and amplification. Reed is really, it's a really nice example of how technology is driving, the ability to answer new questions. This is really key to making these systems cheaper with higher channel counts and smaller. So we're very grateful for his efforts in this domain. So we're using these in a mouse virtual environment, similar to what you've heard about today, only here we very much care about visual stimulation. This is a running wheel. The mouse sits on the running wheel here. It's also head fixed, at least in the current experiments. And here's an example of a pink noise mapping stimulus. It's an immersive dome. It has both visible and UV light because mice see in the UV. Half of the cones in the mouse are UVA sensitive. And this is the sort of, the mouse can run on this wheel and we can create cohesive visual stimulus to study the visual parts of the brain. Another important innovation in terms of getting these devices to work, we want to put 10 or 20 of these in a mouse. It's hard enough to get one of these things working. Getting 10 of them would be virtually impossible. So we've sort of resorted to doing robotic stereotaxic, where we can actually make tiny 100 micron burr holes in the mouse's skull. The drill actually knows when it's got through the skull, so this is not done by hand anymore. It stops on a dime. We can do this reproducibly. We have other piezo robots for implanting the probes gently in each one of the locations. And this has really been something we've only been working on for about 6 months, and it's really been key to this sort of scale up to get reliable recordings from multiple brain regions. Here's one of our first recordings from 4 probes. There's neural activity on every one of the probes here. There's 4 probes implanted here. And so this is something that's sort of hot off the press, so there's no data analysis to speak of yet. But the convergence of these various neural probe technologies and robotic surgeries is coming to fruition. Another important component of this technology, which is sort of still in the nanolab stage, is adding an optical layer to these devices. So I've discussed the electrical probes here, but it's also possible to pattern waveguides with light ports for activating local populations of cells that are optogenetically encoded populations of cells, rather than the current status quo, which is to put a fiber on the head and light up whole brain regions. This is a sort of finer scale method for studying perturbing neurons on the scale of small numbers of local circuits. The current state of the art in this technology is from the Bujaki lab, where they etch down fibers and painstakingly put them on these multi-shank probes here, which apparently takes several weeks to make one of these devices, and they're only really suitable for rats or larger animals. They're beautiful, but they're not really scalable. By comparison, these waveguides, which were fabricated in Nanolab, are 2 by 3 microns, and by some tricks with the way in which we etch the polymer, it's possible to make little input and output mirrors that are very low loss. So you can actually, instead of having an end-firing fiber here, it's possible to have a light that extends perpendicular to the recording surface of the probe, which is the cells that we want to actually record from. And we can put up to 16 or 32 of these on each shank. We haven't integrated these yet, but this is something we hope to do next year. So in summary, we have silicon probes with high-density recording sites up to 128 channels, and we've just started. They have monolithically integrated flexible cables, and we have a miniaturized head stage, which allows us to record from multiple regions in the mouse with high temporal resolution, full depth resolution. And at the moment, we're on the order of 1,000, where our target is to record from 1,000 or 2,000 neurons. Very briefly, this is another complementary technology, which is part of a consortium with HHMI, UCL, and Gatsby, to take that head stage, which is neat by commercial standards, and even shrink it down another order of magnitude by putting CMOS electronics on the back of the probe shank. So these are extremely high-density arrays. They have up to 960 selectable electrodes, of which you can read out 384 of them at any one time. They have a very long span, so these would be suitable for larger animals. And we've just started getting test data with these. These probes will be, it's part of a 20-month project, and by late next year, we should have the final stage devices available for doing science. So I'd like to thank, in particular, this guy who does all of the nanolab fabrication. He'd never fabricated silicon probes before, and only a few labs in the world ever have, and now he does it in volume after working on it for 2 years. So he's a very hardworking, brilliant engineer. My collaborators at both at UC Berkeley and at the Allen Institute for Brain Science, who are doing all the biology recordings with these. Also IMEC and Reed Harrison at Intan, and of course our funding support. So to my mind, the challenges ahead of us are not actually going to be limited by the engineering, as I think we've heard this morning. It's actually data storage and data processing is not going to be the major limitation here, thanks to GPUs and parallel computing. The limitation, the real challenge in making sense of this data is how we're going to visualize it, manage it, mine it, spike sort it, and how we're going to go from sort of pairwise correlations to sort of much more sophisticated dynamical analyses. But the data's coming, or the data's here. So thanks.
All right. Thank you.